Miriam, I was thinking yesterday, what if the facade is in a seismic area? Does it change anything in the design?
Yeah, it probably does. So you should absolutely respect it during your design. But I'm not a seismic expert.
So
I know.
usually a facade engineer is not always knowledgeable about seismic.
No. So this is a very specified area, and we need expert for this. I know one.
Ah, really?
Yes, and I just saw that she's working over there. So let's have a look.
Whoa, what a coincidence. Let's go.
So, Alessandra, let me introduce you to Simona. Simona is a seismic expert at the TU Delft. And Simona, this is Alessandra.
Nice to meet
she's designing a facade in a seismic area. So it would be very nice if you could help her.
Sure. No
Thank
problem.
you. I get a seat. I take a seat, sorry.
Yep.
So, thanks for your time.
No problem.
We are designing a facade, and maybe there is a chance it's in a seismic area. Does it change anything in the design of the facade?
Yes, it certainly changes because we should consider the seismic demand for the design of the facade components. For example, when you are in a certain seismic zone, you should consider what is the so-called peak ground acceleration you have on the building, and then based on that to simulate the behavior of the building, understand the floor accelerations, the floor displacement, and what is their impact onto the facade. So based on this demand, this part should be integrated into the design. And this might change, of course, also the detailing of the different connection system, of the geometry of the facade, especially the thickness of the components, because if you have, for example, a lightweight panel, this means less inertia force, which is better from a seismic point of view. So it is certainly important to consider all these aspects.
So effectively, being in a seismic area means that seismic loads are acting on the facade, and as you're saying, this implies forces and accelerations on the components, which needs to be taken into account. You were saying that the inertia of the facade plays a role. So can I ask you, what type of potential displacement you have in a facade? Because usually in wind, we are looking at out of plane. What happens in a seismic?
Yeah, in case of an earthquake, imagine that when you have a shaking, this is a three-directional movement, which means you have actually both in the out of plane, where the inertia force plays a big role, in the in-plane, where it is important to consider the displacements, specifically the so-called interstory drift, which is the difference between the displacement at the different stories divided by the height of the floor, which is very important for us in seismic engineering. And you also have a vertical displacement, which might impact and affect a lot the movement of the facade. So all of them should be accounted for.
So in terms of the design, this means, of course, it's an implication of what components you select for the panel itself, but I can imagine this affects a lot the design of the connections.
Yes, absolutely. I have to say that it depends on the type of facade, because if you have an external cladding, the design of the connections is fundamental. But in that case, we can have a sliding connection, a tie back, and also dissipative connections, which can contribute in dissipating the energy during an earthquake. While in case of an infill wall, imagine that the infill wall is bounded directly to the structural frame, and this means that this is also contributed to the strength and stiffness during the earthquake of the entire building. In this case, well, it is important to understand and to try to minimize the interaction with the structural system. So to think about the bounding to the structural part, maybe including some internal gaps or other connection detailing.
So there are several things to bear in mind and several alternatives. How do you select a component at the end?
Well, the study starts with, let's say, creating a simulation for the building. and understanding what are the different options, analyzing all of them, considering based on the specific location we have a certain range of earthquakes that are considered, considering the magnitude, the distance from the fault, and all these different earthquakes are included into our simulation.
So there is no one earthquake in the design?
No, indeed, because there's a large difference in terms of expected intensity, for example, magnitude, moment magnitude, as we call in seismic engineering, but especially in terms of frequencies, because an earthquake is typically represented by means of acceleration time, and we do have, based on an earthquake, a different range of frequencies that are impacting also the facade. Each component in the building has its own natural frequency, so based on where we are, we can have a resonance on the components.
Wow.
Which means the seismic demand can increase, can be amplified to the displacement and the acceleration.
Imagine I'm able to evaluate more or less the range of seismic actions, earthquakes that might impact on my building, and then I already have a selection of components. What do? You quantify the damage then, and you decide to take the one with the least damage?
Yes, indeed. It depends on the performance objective that we have for the specific project, but we typically have, imagine, different several options for the facade. So for the building, we understand what is the impact of the range of earthquakes indeed in terms of damage. We quantify this damage, and this damage, which is typically represented by means of mathematical formulations, can be converted into the so-called expected losses. We have both economic losses, which means if you have a certain damage onto a component, what is the repairing action that you need, which means a certain cost, but also indirect cost. So if that component should be replaced, what is the indirect cost in terms of business interruption of daily activities within the building, plus social impact. We have injuries and fatalities, maybe due to the detachment of a panel, and also environmental impacts, because you need indeed to repair the facade, which means also a negative impact for the environment and all the related CO2 emissions for the repairing.
So in case of earthquakes, which are extreme events, I see that in the design process, from the beginning, we consider the fact that it may happen, it may be damaged, will be repaired. So also, it's not only the loss and the damage, but also the repair then that has to be considered when selecting the optimal component, depending on the design objectives, of course.
Yes, absolutely. And indeed, as a further step, what we are trying to achieve, especially from the beginning of the design process, is to create resilient components, which means defining, using this indirect impact to create our resilience, to quantify the resilience of a specific facade. So when you have an earthquake, what is happening is that you have damage, which means functionality drop. After the functionality dropped, which is representing your facade, which is not anymore 100% functional.
Loss some performance.
Exactly, there's damage. Then you go there, you do post-earthquake inspection, so you understand the situation, and then you understand, you mobilize the engineering works, the contract mobilization, then you start with the repairing. So
and this takes time, of course.
Exactly, we call that the recovery part of this so-called resilience curve. And we try to achieve by this repairing the same functionality state that you had at the beginning, or even better. And this is very important for us, because in this way we can quantify the resilience loss. So we try to maximize resilience during our design, which means reducing this resilience loss.
This is very clear to me now. So is it about, in the design process, is it as easy as just doing a compliance check, or there is the need of some more bespoke assessments?
Well, it is fundamental to do experimental testing.
Like to check the performance.
Exactly. This is what is typically done, and we are actually now also trying to improve the current testing protocols, because what we typically do is using a specific input to be simulated by means of the experiment, and to check the serviceability and the ultimate limit state of the facade.
So both service and ultimate state.
Exactly. In the serviceability, it is important to understand at which drift intensity, interstory drift or acceleration value we have loss of functionality for the facade. So for example, you have after a low intensity earthquake, the loss of air tightness for the facade.
Lose air tightness because of
Yes.
the potential damage.
Or you have water penetration,
Water penetration.
inside the facade. While at high intensity earthquakes, you are interested in understanding what is the expected damage onto the component and what is the maximum level at which you have failure, which is fundamental. If it is, we typically focus indeed on interstory drift. If it is at 2%, 3%, this is also changing the design of your component.
And do you have a video of a test, how it looks
Yes,
like?
I can show you a video on a shake table, which means imagine you have this big platform where you can connect your facade. But in this case, as you can see, we have an entire building, which is a concrete timber building where we connected both the glazed facade on one direction and we have external concrete cladding in the other direction. And as you can see, we included high performance connection detailing plug and play solutions, which are flexible, so easy also to be replaced after the earthquake if we want to change the configuration of the facade of the building and so on. And as you can see, this has very potential, so we call them low damage technologies, and these can be used to create very resilient, integrated structural, non-structural solutions for buildings.
Very interesting. And my last question.
Yep.
So in the design process, when is that the seismic engineer should start to participate in the design of the facade?
From the very early stage of the design process, we need to work together with the architects, structural engineers, to understand if seismic considerations are included into the design. Even in terms of building a geometry, the layout.
Okay, so really early design stages.
Yes, exactly. And then, of course, we can start with doing some calculations to understand the forces, what is the structural system to be used, the material to be used, the strength, the stiffness which are needed, and then continue throughout the whole process with the detailed simulations of the connection detailing, and then moving on with the experimental testing for the seismic certification of the facade.
Thank you. I think that this is very clear to me that when designing the facade, as a facade engineer, I have to go to the seismic expert as soon as the design process starts to include these considerations. These are not calculations I will do if I'm a facade engineer, but I will go to the expert. So it's important that these concepts are quite clear so that we know when including the right expertise at the right moment. Thank you very much.
No problem.